All right, so we're going to go ahead and start talking about another area problem. So this is example 2 of finding polar area. So we're going to find the area inside one petal of the curve r of theta equals 3 cosine 2 theta. So the reason I said one petal is this is one of a variety of curves that creates what's called a rose curve. So a rose curve essentially looks like a flower, which is why it's called a rose curve. So if I graph this for you, so I put in my polar mode, I put in my R1 as 3 cosine 2 theta, right? When I zoom, I went to zoom standard, which was zoom 6, right? And what you'll see is I get a curve that has petals, in fact 4 of them. Now they don't look particularly symmetric. The reason they don't look symmetric is because the calculator itself is not a square, it's a rectangle, right? So the petals going left and right look longer than the ones that look kind of short and stout that are going vertically. If you wanted to see that they are symmetric, you could pick zoom 5, which is zoom square, and it would show you that they are in fact symmetric petals, right? I don't think that it really matters that we see that, so I'm going to go back to my zoom 6. So the trick here is that I have 4 petals. There are a couple different ways to do this, right? The window, you're going to have a calculator in this situation, and there are a few different options. You can do any number of ways to figure out what one of these petals is. I would say that the easiest way to find the bounds for one petal is that for a petal to start and end, the radius, this r, has to be 0 because the petals both start and end at the pole, right? So the easiest thing, in my opinion, to find the area of one petal is to find essentially bounds of when the petals start, right? So when I want to find these bounds, I essentially want when r is 0. So if 0 equals 3 cosine of 2 theta, 0 is the cosine of 2 theta, and I say to myself, oh, well, this is the x on the unit circle. It equals 0 at all the pi over 2's. So 2 theta must be all the pi over 2's, right? So it doesn't really matter which direction you go. Like, you could go plus or minus, right? But it's plus or minus pi over 2 and 3 pi over 2. And I generally recommend that people go around twice, and the reason I say that is I'm about to divide all my answers by 2. So if once around the circle would be a pi over 2 and a 3 pi over 2, I'm going to go around again and do a 5 pi over 2 and a 7 pi over 2. But for the record, you could keep going with this. These bounds go on forever. So essentially, if I want to find the bounds of one petal, I divide all these guys by 2, and basically I'm going to pick any 2 adjacent bounds because they will be the start of one petal and the end of the previous petal, right? So for me personally, I'm just going to go ahead and go with the ones that seem kind of lazy. I'm going to pick the petal that starts I'm going to do the one that's right here, meaning it's going to start at pi over 4 and it's going to end at 3 pi over 4. So that's the petal I'm going to look at. It doesn't really matter which one I pick because I just asked you to pick one of the petals. So if you look at my graph on the calculator again, I'm picking this one right here. What I would say is if you had chosen, let's say, this one, the thing you have to be careful in picking this one is that your bounds are negative pi over 4 to regular pi over 4, right? They'd have to be the adjacent bounds that fall in this category. So again, it doesn't matter which one you pick. You could have picked any of them. It's a circle that goes around and around and around forever. I happen to pick this one. So once I've found my bounds, right, which seems like a lot of math, but it's not awful, I realize that the area inside a polar curve is 1/2 the integral from whatever my first bound is, which I chose the pi over 4, to the last bound, which was a 3 pi over 4. Of my r squared, which would be a 3 cosine of 2 theta whole quantity squared with respect to theta. So this is my job to set this up, right? And I know you probably lost the end of it on the thing, so I'll scooch the board over so you can see my d theta. Once I have that set up, great. I don't have to integrate it by hand. This is a category of a problem that you probably could be asked to integrate by hand using some power reducing formulae, but we're not going to right now. I can show you in a second how we'd integrate it by hand if you want. So I put this guy in my calculator as my R1, right? So what I'm going to type in my calculator is 0.5 function integrate of my R1 squared with respect to theta from pi over 4 to 3 pi over 4. And again, if you chose 2 different bounds, if you chose negative pi over 4 to pi over 4, it would be the same answer. It doesn't matter. The petals are all symmetric. So if I quit out of this, right, I'm pretty sure I just did a trig. So all I'm going to do here, I just did a polar formula a second ago with you, so I'm just going to change my bounds because I am a lazy bum. So I'm going to change that to a 3 pi over 4. So I've got a 0.5. I've got my r sub 1 quantity squared with respect to theta from pi over 4 to 3 pi over 4, and I'm going to hit enter, and I'm going to get my answer, right? So my answer ends up being that the area of that one petal is approximately a 3.534. That's the area I want, right? Again, the AP is going to want to see this set up. They're going to want to see you find the bounds, whichever set of bounds you found. and they're going to want the final answer. They're not going to need the stuff that I wrote in red. Anywho, so if you want to stop listening to this video right now, you can. I am going to show you how I would do this if it was a non-calculator question. Again, you can totally feel free to stop listening to me right now if you want. So if this were a non-calculator question, I do all the setup stuff the same, but if I didn't have a calculator to lean on for this, I do have a few options. I will say that if it was a non-calculator question, I would not have picked the bounds I picked, and I'll walk you through why in just a second. So if this were a non-calculator question, right, if this were a non-calculator question, I would have picked these. And the reason I would have picked these is because the other thing I want you to spot is that this pedal is symmetric. So what I would have done is I actually would have found the area from 0 to pi over 4 and doubled it. So if I were doing this on a non-calculator test, right, I would have recognized that this area, right, 1/2 the integral from negative pi over 4 to pi over 4 of the 9 cosine squared of 2 theta, right, d theta, is the same as double the area if I go from 0 to pi over 4. So I would have just said, cool, I'm going to integrate from here to here. And you might say, but Hogan, how does that make it better? Well, it makes it better because plugging in 0 is always better than plugging in not 0. All right, so then the next issue I run across, if I'm doing this by hand, and again, I get if you just turned the video off and said, hey, I'm not going to do this, I'm not about this life, that's fine. The problem I run into next is that I need essentially what's called a power reducing formula, because I can't integrate a cosine squared outright the way it is, and the only trig identity I have that relates a cosine squared normally without thinking outside the box a little is sine squared plus cosine squared is 1, which doesn't really help me. So I'm going to have to look at the cosine of 2 theta formula that we learned sometime in pre-calc at some point probably. So cosine of 2 theta equals 2 cosine squared theta minus 1. This formula can be repurposed and moved around to make what we call a power reducing formula. If I solve this formula for cosine squared, I'd add the 1 over and I get 1 plus cosine of 2 theta all over a 2 is my cosine squared theta. So this is what we call a power reducer, right? So if I were going to do this on my own, right, I could take this cosine squared that I don't want and I could use this formula to reduce it. So what would happen if I use that formula? Notice that here inside my squared is a 2 theta, not a theta. So what's going to happen when I apply this formula is if I take this 9 cosine squared of 2 theta, and I'm just going to do work here for a sec without the integrand. If I take this guy, right, and I use this formula, I get a 9, and then in place of the cosine squared, I get a 1 plus cosine of double what theta was. Well, my theta here was already a 2 theta, so I'm going to get a 4 theta all over 2, no more squared. Excuse me, I need to get a drink of water. So, much better. So, if I clean this up a little, I now suddenly have a thing that I'll be able to integrate. I have a 9 halves, which is easy, it's just a 9 halves, plus a 9 halves, a cosine of 4 theta, which is simple u sub. So this is what's now going to go inside my integrand. So if this is my work for a sec, right, I'm now going to take the integrand I had, so I'm going to erase my power reducer since it's a video and you could always go back if you need it, right? And I'm now going to go back into my integrand, and I'm going to make this guy, right, this integrand, into the integral from 0 to pi over 4 of a 9 halves, right, plus a 9 halves cosine of 4 theta with respect to theta. Well, now this is simple u sub that I'm actually able to integrate by hand. So to give myself a little bit of space, I'm going to erase pretty much all of this stuff and just give myself a lot of room to work. So what's going to happen is if we recopy up here, I'm going to get that my area is the integral from 0 to pi over 4 of 9 halves d theta, which is a straight up power rule, plus, not an equals, plus the integral from 0 to pi over 4 of a 9 halves cosine of 4 theta d theta. So, and that means I can now erase this. Okay, so my area ends up being a 9 halves theta, right, because that's what 9 halves d theta would integrate to. This is technically u sub, right, where my u is 4 theta, but logically what's happening is every time I derive a cosine of 4 theta, I'd have to times by 4 in addition to deriving the trig function. So if I'm integrating, I'm going to have to divide by 4. So I'm going to get a 9/8, and when I integrate cosine, I get sine. So I'm going to get a 9/8 the sine of 4 theta, and all of that is going to be evaluated from 0 to pi over 4. So that means that my area ends up being when I plug in pi over 4, a 9 halves times a pi over 4, which we'll deal with, plus a 9/8 times a 0, because I'd get sine of pi, minus what ends up coming out to be a 0, plus, and then I'd end up getting sine of 0, which is a 0, right? So after all that, I seem to get that the area ends up just being a 9 pi over 8. And if we do a quick double check, remember that the answer I got before was a 3.53 something something something. And there, you'll see both my answer from before and also the answer we get now is a 3.534, which is the same answer. So you don't have to do this by hand, but when you're asked to do polar area by hand, it is very, very often going to end up using that power reducing formula. And we'll go over that in another video.